Well, good afternoon, everybody, and welcome to Ellensburg, Washington, USA. It's 11:45 a.m. Pacific time on a Friday, a gorgeous Friday, and we will begin this lecture in about 15 minutes from now. I'm hoping you can all hear me. Could I get a 5x5 from some of you, please? And if not, we've got problems, and I'll have to go ahead and, there we go, Garrett. Thank you. Thank you, you guys. Okay, so let's stick with the title slide for just a second and say welcome, especially those watching this in replay. You can go ahead and skip ahead 15 minutes because we are live right now and this lecture will not begin for 15 minutes. But I'm going to switch around to the other camera and say hi to a bunch of folks who are watching live from all over the place. And as always, what a relief to have that audio working. It always feels like a 50-50 proposition. So I can set the stage and welcome you all. We have more than a few minutes to just settle in here. How's everything going with you? I hope things are going well. And now that you can hear me and see me and we're connecting live, let me say hi to a whole bunch of you here. It's a gorgeous day here. It's been 80 degrees Fahrenheit the last few days. Gorgeous spring weather. It almost feels like summer weather. Everybody's going out in the field, and so we have a rare chance where people are back here in the building, in between field trips and everything else. Let me scroll back. I think I've already missed a few places. Hello, Dayton, Ohio, and Springfield, Oregon, and Minneapolis, Minnesota, and Modesto, California, Dorset, UK, Wickenburg, Arizona, Lake Chelan, Washington. Hi, Laura. Payson, Arizona, Deering, Kansas, Salem, Oregon, Half Moon Bay, California. Hi, Jason in Wenatchee. I'm heading up to Saddle Rock tonight, Jason. Filming with a new guy in PBS. Nick on the Rocks is back happening again. We're doing a Saddle Rock episode. So he's got a drone, but he's probably not as good as you, Jason. Hope he doesn't see this. Villages, Florida. Paris, Illinois. Hello, Carol. And Gracie, I believe. Gracie's maybe in school. There's Michael in Ireland. Michael says, hi, Nick, Carey, and everyone from me and Nee watching. Hello, Nee, over there in Trim, Ireland. Tri-Cities, Washington, and Marion, Virginia. And that's Carey and Hannah Shamloo over my shoulder. So we will be concerned about Carey's microphone in just a few moments. In fact, let me just pause for just a sec. Yeah, we're not going to bother with your mic yet, but we're still good here. Everything's identical to what we were just talking about. We're fine. So I'll turn your mic on in like 5 minutes. How about that? Okay. All right. Go back again. It's been a while. I haven't been live with so many of you for quite a few weeks now. So if I'm just being selfish now, it's just a thrill to see so many of you back here. Ben is in the Netherlands. Garrett, the Dutch Night Owl, is the Netherlands. Thorpe, Wisconsin. Come on now. And Therese from the Netherlands. Washougal, Washington. Port Wing, Wisconsin. Hi, Andy. Kennewick, Washington. Mojave. DeForest, Wisconsin. We got plenty of Badgers here. Renee is in Quebec. Shoreline, Washington. Peridot, Arizona. Lincoln City, Oregon. Hi, Doug. Montlake Terrace, Washington. That's in the Seattle area. Florida. Bergen, Norway. I'm down to live now. Guilderland, New York. Kamloops, BC. Ben's giving us a weather report on the spring weather in the Netherlands. Cleveland, Ohio. Park Falls, Wisconsin. My God, we got Wisconsin people out of control here. Dick is from the Netherlands. Hi, Dick. Hope everything's going well with you. Boulder Creek, California. Wichita Falls, Texas. Pittsburgh, Pennsylvania, and so on. Okay. So I don't know. Let me just say a few extra words here, since many of you have been regulars with these live streams over the last few years, and since it's been a little while, we've had an amazing stretch of weather. I've been teaching Geology 351 and posting just a few videos And I think there was just one live stream involving Jerome Lessman. So if I had built up the 351 this spring as some sort of regular thing like I did 2 years ago, I'm sorry, it didn't happen that way. There's a number of reasons for that, but the primary reason is we were building towards Jerome Lessman visiting us and Sky Cooley and Joel Gombiner, and I wanted to devote most of the attention to those guys and put less energy into capturing all of this. There are some Geology 351 papers that we have been studying, and they are available to you if you are unaware of that. If you go to nickzentner.com, 351 in the upper right-hand corner, there's a handful of papers that we are reading this spring. And they're available to you. Some of them are brand new papers, Ice Age Floods papers, including a PhD thesis by Joel Gombiner. But I just have not been regular, as you know, with the YouTube channel. And I guess I'll continue to be vague about that. But anyway, I've missed this for sure. And we have just a few weeks left in the term. And the weather's gorgeous and everybody's burning out, including yours truly. And so I think this summer I'll have some things up my sleeve, but not until we wrap things up in early June here for the academic quarter. Okay, that's enough of me. So thank you. We check one more time that we're okay, and then we'll make sure that we transition to our speaker here. So are we 5x5 still with my microphone before we go to Carey here? Thank you, Michael. Okay, good. Okay.
Will turn me on?
Turn you on.
Stop talking.
Yeah, now we can't talk about
I gotta find you here.
the ancient.
There you are. Good. Okay.
We're talking about all the answers to our final.
Oh, good. Yeah. What is the answer to question 3 on the final? And can we then give the link to these guys so they can see what's
Yeah.
going on?
What is the answer? Alpha, yeah.
Okay. All right. What's your birthday again?
July 13th?
July 13th. 7 days older than me.
Yeah.
Hey, cool.
Hey.
Isn't that scary?
How we doing? Can you hear Carey okay? Carey's 5x5? Thank you, Garrett.
They can hear me?
They can hear you. All right, we'll just keep it on if you don't mind people listening in your chit chat here with Hannah.
But it's all the answers to our final.
Yeah. And you remember that once we get rolling, I'll say just a few real quick words, and it's hardly anything because I don't have any talks to announce except Max's talk. And I'll be very brief with my intro, and we'll just go for it with you. Okay.
Yeah, I'm excited.
Okay, let me swing you around. We have the room
I had fun putting it together.
filling in now. Nice turnout for such a gorgeous day. And thank you for joining us.
It's nice to see
If you just joined us and you're like, what's going on? When are we going to start? We're going to start at noon. And that's about 7 minutes from now. Watching in replay, you can scrub ahead 7
We
minutes
don't know what he's
to
telling
the beginning of the lecture. Thank you for joining us, everybody.
So the lab's almost done. So excited. Thank you again for letting me invade your space.
No, it's all right. I'm trying to figure out, how that, because there's another room.
Yeah, okay. So you can divvy your stuff there.
Yeah.
Appreciate it.
Yeah.
Well, we got to get Chris Mattinson in there.
It's exciting.
Yeah, we were trying to cross it. We've done the past 2 weeks. Water.
Special shout out to Carey's mother if she's watching.
Do you want to see my exam when I make it?
I guess, but I'm not I don't need to, not that I'm gonna, I'd just be curious.
Okay, yeah, awesome.
Yeah. It's a good group.
No, I really like it. Good energy. And it's, I think we're doing a more than this.
So this is your break or schedule a sub?
My break.
Nice.
I'm a part-time guy.
I think that there's times when
Works
students
out.
just
Good.
Yeah, I get to do interviews.
Gives you the
I have
heads
no
up.
idea how to do it.
Yeah, exactly. So it's like the fact
It's
we're
like,
there.
yeah,
Try to
I think
climb
that could take hours.
Oh, yeah.
100 highest peaks
100
in Washington
days.
this summer
It's
using
figuring
only
out what to do.
power and transportation. No cars or boats or fossil fuels.
Holy cow! Really? 100?
So the route is still in college, but Mike and I went up and climbed 7 up in the campus this weekend.
What are you doing?
Gotta go
Um,
this weekend I have district track.
working a bit.
But
I'll
next
go to
weekend,
Maine.
try to go do Stewart, Sherpa, Argonaut,
Maybe some local
and then
trips.
How's the snow on
we have
the
reservations
I
on
mean,
Rainier for both the end of
there's
Memorial Day and the
definitely
next
the
weekend.
one project I'm
Unbelievable.
talking about.
Holy
The,
cow!
And then
the
once
salt one,
summer
I'll have to
starts,
work
let's
on
go
that
one
for
big
sure.
trip. There's a map on there.
I'm going to go here. This is Instagram and this is just the website. Yeah.
Jeff is doing a big trip.
Very cool.
He's gonna go. The other.
Yeah. Okay. Yeah.
Looking forward to this.
Oh, good. Me too. Sort of.
I think you got a nice tan right now. You been out?
I've been out. Thank you. I'm laying out.
Really?
People's Pond. Just kidding. Reading my novels. No, just come on, man. Yeah,
Walking
going
around.
out with these students.
Feels good, right?
Cyan passed out yesterday at
Really?
dressed in black. So hoping to find him
No.
today. Check his pulse.
Yeah.
Top 3 impressions from yesterday. Top 3.
It was the first time that I was able to get a good overview of what you mean by crinkle, like the crinkly ring.
More
Yeah.
weighted towards the back of the room.
So that was
The
Yeah.
back rows are pretty much full.
I know all
Yeah. I must admit that I end up in the back often.
what that tree was called.
I come in
Wait, you sat in the back when you were a student?
I don't know.
as a student, I did.
Really?
Well, as a grad student, no.
Yeah.
But as an undergrad, for sure. Or maybe the middle
Yeah.
back.
For the ranch.
Yeah.
I was in the
Maybe it's because you're short.
I'm short in my eyes. I have bad eyes. I wear like I have like negative
It's just-
vision.
First
I'm not
stop
gonna read my glasses. I don't have my glasses in.
that was the first time I've actually seen Zentner in person. So I thought that was kind of cool.
Yeah.
Maybe I don't have
But the current ripples aside,
No,
what
I
we
don't
would
need
start
to.
discussing later
Just in
on.
case.
Is that I
Reading
think I agree
glasses.
with you now, like current ripples were cool, but it was almost more impressive to see the sheer size of the basalt columns and how that side was just so much more exposed than the other side that we were looking at.
I was telling Nick that I think making this 304 class.
I'm very happy with what you just said.
It's
It's almost like I was recording it right now. I'm gonna play it back over and over and over again. No, seriously. Thank you. Yeah, I mean, that first thing with the pre-glacial mature landscape, I wasn't planning on that, but I think that has to be what I
And
do.
yeah, and just
Yeah.
the community.
Yeah.
like, yeah, like I said, spent class twice now.
Can't quite.
Yeah.
Yeah,
Like what
Right.
I mean, just to
Right.
represent.
and the scale of that too. I mean, like
I never
you're
went to
trying to
anything
visualize
else.
like a football field or something. No,
That is when I was looking at grad school. And I was told you need to go to this talk.
Yeah. Just being able to see crinkly wrinkles, but how flat.
Yeah.
That was
Good. Thank you for that. 2-minute warning.
2-minute warning. I know. 2
You,
minutes to
you've
watch.
done this. Yeah, you did.
Yeah. It
It's a
was
little bit
fun.
different.
It
Yeah.
was nice because I didn't get proper dissertation defense.
Good.
Because of COVID.
Because of COVID. So my parents got to see me
You
give a public
interviewed
talk.
right before, like
Can you
days
literally days
before.
before the
Yeah.
world locked down? That was crazy.
Were we like spread out in here? I think
No,
we
you
were.
guys, we were in 206.
There was one after you where we were spread out.
Oh shit. Yeah.
It was probably like the day
That's
after you. I mean, it was going downhill, right? Yeah.
I had such a good time
Crazy.
here. I was like, I want this really bad.
Wow.
I know it's so weird to think about. Actually, get silent. Yeah, I was very nervous for that interview.
Keep it quiet, Hannah.
Yeah.
30 seconds.
Countdown starts now.
Oh, my watch says noon. I better go. No.
Got it.
So just start.
All right.
Waiting for Nick.
All right, I'll take my cue. Everybody ran out of small talk, huh? Interesting. All right. All right, well, let's do this. Okay. Wow. All right. Welcome, everybody. It's such a gorgeous day. I'm so glad that you're here. We've got a full room on a Friday towards the end of the quarter. At least it feels like the end of the quarter with the weather. So thank you for being here. We only have one more of these Friday talks this spring term, and it's June 2nd, the last day of regular classes. So we're not doing this again for 3 more weeks, but I'll see you on Friday, June 2nd, and Max Nito will be here. He's not normally here on Friday, I don't think, but he's been doing a great job with our structural geology class, and he's giving a talk. I've already announced it a few times, designing video game style field geology simulations for research and education. So that will be a way to finish our year-long series of these Friday talks. So for those of you who have been coming to every one of these, I'll have a special sticker for you on June 2nd. What? Okay, so, right. Our speaker today has been here many, many years. A few of us have been here more than 25 years, and our speaker, Carey Gazis, fits that category. She has had more than 20 graduate students studying groundwater geology, aqueous geochemistry, and 30, 40 undergraduates under her tutelage over the years. So there's a lot of hand-to-hand combat with students over the past 2.5 decades. And we are thrilled to be able to get a chance to hear directly from here. Just one final note before we turn it over to Carey. It was on purpose that when we put these speaker schedules together, Hannah Shamlo and I, that we wanted a mix of guests and also our own folks. And I think it's fair to say that many of us have not heard direct talks from some of our faculty. So this will continue next year as well, especially in wintertime, but it's by design. It's on purpose that we get a chance to showcase some of our own folks as well as people visiting us from other places. So today's talk, groundwater storage, a sustainable water management solution. Please help me welcome Carey Gazis.
Thank you. I'm going to get started. I want to start out by acknowledging my collaborators. And this is related to groundwater storage. First of all, Lisa Ely. Many of you know Lisa. We've worked together for years on this, and I think our expertise really works well together. There's synergy there, and I appreciate having a collaborator so close by. She's 2 offices away from me. And then there have been, I think there's 10 graduate students there that have worked on this. I'm not sure. And a number of undergrads as well. And we've even had classes involved in this research. The students there in blue are the ones who, I'm going to talk about 2 particular projects related to groundwater storage. And the students in blue are the ones who have really collected some of the data, made some of the interpretations that I'm going to present. I also want to point out that 3 students that are working on this research are going to be presenting their master's theses soon. Emily's presenting next Monday, I think, Bethany on Tuesday, and then Lindsay the following Tuesday-ish. So hopefully you'll be really excited by the end of this talk, and you'll be excited to go hear 3 more talks about similar topics. I'd also like to acknowledge my collaborators outside of CWU. We work with a lot of external organizations and entities, but in the 2 projects I'm going to talk about, the main collaborators have been Mid-Columbia Fisheries Enhancement Group, Kat Strathman, and then 2 consulting firms, Coho Water Resources and Geosyntech Consultants. Finally, the research I'm going to talk about today was all funded by the Yakima Basin Integrated Plan Groundwater Storage Subcommittee. So to start off, I want to tell you why I'm excited about water. as I was thinking about water, I started thinking about the hydrologic cycle, and then I started looking on the web for a new and different hydrologic cycle. And I found this one, which is from the USGS. It's their kids version. And my first thought when I looked at it was that it was kind of scary to me as an adult, but maybe not as a kid. But then it grew on me, and it shows the water, essentially molecules, as these little droplets that interestingly have emotion, it seems, and they do things like picnic on top of a tree, which is kind of cool. But it also shows the ideas that I want to get across. One is that water is constantly going into and out of the atmosphere. That's the idea of the cycling. And this process cleans the water as well. And then important to us, a lot of it falls out of the atmosphere as snow in the mountains and then works its way back towards the ocean. And the cycling means that it's renewable. It's considered a renewable resource, right? But the problem is, in an arid place like this, we have a lot, we've created, or we have a lot of needs for fresh water. And even though it's cycling, we don't have the fresh water to meet all our needs. But there is certainly the potential for sustainable management practices because of this cycling. And then it also flows through the ground. And I want to call your attention to that section of the diagram. It's pretty cool. So the groundwater, they show it as kind of getting sleepy. Here it looks a little sad, which I don't think it should. And then it goes to sleep, and then it wakes up and has some coffee, and then it dives off into, I think, the ocean. But anyway, what they're trying to show here is that it slows down, right? And that it can stay down there for a while. And we will talk about that. Okay, now I want to really start my talk by talking about the history of the Yakima. And in doing so, I want to acknowledge the indigenous people that have lived here since time immemorial. So I want you to spend a minute just thinking about what the Yakima River Basin was like, to someone coming in here before all the roads, all the pavement, even the farms, what it looked like. And this is the Yakima Basin in the slightly darker color. And if you looked out to the west, there were mountains, right? And then forests, denser than they are now. And that was a good place to go up and find different edible plants and to hunt, especially in the summer. In the winter, it was kind of formidable. And then if you looked out on the east side, you have these ridges, right? The Yakima Fold and Thrust Belt. And in between them, you have these valleys, and it was dry, right? This part is agriculture, that wasn't there. It was dry. There were some streams coming through with riparian zones around them. It was a good place to seek shelter in the winter. And importantly, there was this majestic river running through the middle of it, the Yakima River. And the Yakima River was great for transporting things, and it also had this amazing supply of tasty protein in it, the fish. So within the Yakima Basin, there were actually a number of different indigenous groups that moved in and out. This is from Native Digital Lands. It's a database of where they're trying to recreate basically the territories of the different indigenous groups. They'd spend their winters on the valley floor. And then in the summers, they'd move up into the hills to gather plants and to hunt. Some would stay by the river to continue to fish. And this is maybe what it looked like. I showed this to Lisa. We spent a while on Google Earth trying to find that stream cut, and we decided it's not there anymore. And fish, again, was a big part of the lifestyle. This is drying fish, a Native American woman. Then in 1855, there was a treaty that was pushed the people onto a smaller piece of land. So at that time, I guess they decided what was being ceded. And I really want to find the story about the shape of this thing. But anyway, the ceded land for the Yakima Nation is this larger shape. And then this is the reservation that they currently have. And the Yakima Basin is entirely within the ceded land. So, I mean, you look at that, and you can tell that it was rough to be pushed into that small area. But one thing that did exist in the treaty was the right of taking fish. The words are right of taking fish at all usual and accustomed places. And that ends up being important because these guys are here since time immemorial, right? And they have a right to take fish at all their usual places. That actually is the earliest water right. Then the white European heritage settlers moved in. And one of the things that they did in the early 1900s was really pretty intensively log the forests. And part of that process, they removed large amounts of wood, and to get it out, they used the streams to transport the wood. So this is actually the Channaway River. And those are some wood that they're getting out using the stream. And this process, and then they created railroads later to get it out. And between the railroads and the transporting on the streams became incised and channelized. And you'll see that in the Channaway River in particular, it's been incised into the bedrock. Around the same time, some of the settlers decided to farm. And I really like this picture because I look at it and think, what is this guy thinking? You know, like if I was choosing a place to farm, that wouldn't be the spot. But he knew that they could get water out to that spot, that there was plans, they already knew how to make canals and bring water from the river into these dry areas. And so that continued and still continues. But an important date in the history of water in the Yakima Basin, it was 1905, because at that point, the federal government, the Bureau of Reclamations, designed and began to implement the Yakima project, and they claimed all unappropriated water. So all the surface water that didn't already exist, or somebody didn't already have a right to, they took it. And they constructed 5 storage reservoirs and dams, and here's an example of one. And they basically, that was their water, and they regulated it out from the dams. And the people that took that water are largely the irrigation districts. So there's a number of them moving down the Yakima. This is an example of one. This is the Kittitas Reclamation District. And what they do is they divert water, like in the Kittitas Reclamation District, they divert it from Easton, and then they bring it down and use gravity to kind of bring it around the sides of the valleys. And then they have other laterals, other waterways to bring it onto the fields. And here the colors are just the different ditch riders for this irrigation district. So all this 1905 water went to a number of irrigation districts. So we have the current condition that we have now, sort of. The irrigation districts are in the valleys, right, between the ridges. And they use the majority of our water. And they are classified in terms of surface water user rights. This diagram is wrong. It should have the Native Americans at the very top with their fishing rights. But these are maybe the irrigators. Beneath them, you have your senior water rights. Those are people that took the water out of the Yakima before 1905. The proratable water rights holders, those are the 1905, the US Bureau of Reclamation rights. And those are a lot of the big irrigation districts in the area, including the Kittitas Reclamation District. They receive their full right in non-drought years, but in drought years, they don't get all of their water. And I looked for this year. I, in my mind, thought it wasn't a drought year, but right now, at this moment, they just upgraded, and KRD and Rosa and the other proratable rights holders are getting, at this point, I think it's 86% of their water. So this is actually, even though it seems like a good year, they're not getting all of their water. And then beneath them, you've got your junior water rights holders. They get no water on a drought year. And then, I don't know why that's even there. Someone with no water. Oh, there are people diverting water illegally without a right. So stepping back, we've got kind of two players here. We've got, I mean, there's more than two, but we've got the Yakima Nation, or the fish people, the people that want to keep water in the river and sustain the fish. And then we have the irrigators who are trying to make a livelihood off of using water for irrigation. Here's our next player, climate change. So as if it wasn't bad enough with all the water allocated, we're shifting now from basically from snow, a mix of snow and rain. So here the colors are, the blue is snow dominated, the red is snow and rain, and the green is rain. So historically, the mountains have had snow, but it's shifting now by 2040. So the Yakima Basin is right here. By 2040, there will be no snow-dominated area. And then by 2080, it's predicted to be largely rain. And what that does is it shifts when the water comes out in the river. So that's called a hydrograph. This is an example of a hydrograph. So a hydrograph has some measure of stream flow versus time. And so snow-dominated situation, you have your peak flow is during snowmelt in the spring, right? And then mixed, it shifts by the time you get to rain dominated, your hydrograph, the peak of your hydrograph has shifted to the left there. So this period right here is critical. That's when the farmers need their water. That's when the fish need to not die of heat and need to move around. So this is a concern like this. And then on top of that, your river becomes less connected to the floodplain. So in general, this climate change is kind of exacerbating the problem. So so we've got a situation, water is over-allocated, climate is changing. We have these competing demands, particularly fish and agriculture. And, you know, Yakima Basin is kind of unique in how extreme that was. Luckily, Yakima Basin is actually unique in how we handled it. Like this is one place where Central Washington is at the front of, like, leading the charge in terms of water management, I guess. Because what happened is the stakeholders all got together and they said, we've got to do something. So the Yakima Nation, all the irrigators, the cities, the counties all got together, the federal government, and they came up with a plan called the Yakima Basin Integrated Plan. And the idea of this plan is it's meant to secure the water supply for 30 years. I want it back. Thank you. The plan has 7 parts. And I'm going to briefly explain them, but they all have to do with fish or water supply. There's market reallocation, that's water banking. Habitat, watershed protection and enhancement, so that's really habitat restoration. Enhanced water conservation, that's lining the canals, being more conserving our irrigation practices largely. Structural and operational changes. The big part of this is a pipeline between some of the reservoirs in order to manage what's flowing, where they let it out when, and in order to increase the amount of water in the reservoirs. Fish passage. Surface water storage, there's a plan to actually add another reservoir, and there's also plans to up the level in some of the existing reservoirs. And finally, my favorite, groundwater storage. So that's what we're going to talk about next. Before we do, I want to give you a little background. So groundwater, let's think about that for a second. If you go beneath the surface, you reach a point where all of a sudden all the pore space at that point is filled with water. There's no air in there. So that area down there is the groundwater. The top of the groundwater is called the water table. I will use this term a lot, aquifer. Aquifer is simply a subsurface unit that can store and transmit water. So it's kind of has to be useful to a human in order to be an aquifer. So it's the name of the rock, it's not the name of the water. It has to be able to store water, which means it has to have pore space or void space. There has to be holes in there for the water to stay, and that's called porosity. And it has to be able to transmit water. Water has to be able to flow through, and that's called permeability. And these are definitely related. Usually if something's porous, it's usually permeable too, but they're not, they're different. And you can have something that's porous but not permeable, or permeable but not porous, I guess. Yeah. Okay, the next thing I want to talk about is two different types of aquifers, confined and unconfined. It is what it sounds like. And let's start with the unconfined. An unconfined aquifer is towards the surface usually, and it's an aquifer that basically has the water table at the top, and then the unsaturated zone, or the area where there is air, above it. So this right here is the unconfined aquifer. The water level in a well in the unconfined aquifer rises up to the level of that water table, right? But you can also have an aquifer that's confined. It's got something on top of it that's not letting that water rise up. And that's called a confined aquifer. So the confined aquifer has to have a confining layer or aquitard above it. And the water in a confined, they tend to be deeper. And the water in a confined aquifer is usually under pressure. And so when you put a well into that confined aquifer, the water will rise up to an imaginary surface. This surface doesn't exist except when you put wells in. That is the level that water would go to. It's called the potentiometric surface. The confined aquifers can be regional. Like unconfined aquifers are usually within a single watershed, but an unconfined aquifer can move beyond, into other watersheds. Next, I want to say a word about wells. Wells are the hydrogeologist's magic window into the subsurface. We as geologists, I think, have a lot to add to this field because we think about the subsurface. We think about how rocks are related down there, where there's faults and so on. But it's hard to know what's going on down there with the water, but wells are our window. And they come in all sizes. There's a little piezometer. It's a little small well that we put in with an auger. Here's a big agricultural well. We get to go out and watch them be drilled, which is super fun. We go there any time of year. And we can measure the water level in the well. Here's one thing we use to measure. It's called electrical tape or E-tape. You just put it down the well and you can measure how far down, it's just got gradations on it. So you can measure where the water is. And those water levels tell us about how the water is flowing. They tell us about how much pressure there is in an aquifer. And we can see the water table by measuring the water levels. And then the other thing we can do in the wells, and I'll talk about this more later, is do aquifer tests. And the idea there is you can pump or add something to the well to see how easily water is flowing into that well, so that you can determine whether it's permeable and how much it can store, the aquifer. Okay, so groundwater storage. The idea of groundwater storage is pretty simple. We have this place where we know water can go in the subsurface, and we have to get it in there. There's two main ways that we put it in. I think there's just two ways. One is infiltration, and that in that case, you maybe have a pond or you might have a ditch, and you put the water in there. You have to know that it's going to get in, and if you're lucky, it comes out into the surface at a time that you want it to, or you can also pump it back out. And then the other method is called aquifer storage and recovery, or injection. It's this one is more expensive, and the idea here is you actually pump it down or put it down through a well into an aquifer, and then later on you can take it back out through the same well or by another means. I mean, it might get into the surface. Usually this is going to be more in the unconfined aquifer, and this is going to be more, or would be more likely to be in a confined aquifer, I think, at least deeper. The idea in groundwater storage is there is a time of year when there's plenty of water, and that is in the spring. And here's my example. This is last week in Ellensburg, right? I'm not saying that we'll be able to actually capture this floodwater, but it would be nice if we could. But at that time of year, there is some ecological function to the spring floods and stuff, but in general, there's water that's basically making its way out to the ocean. And if we can get that water and get it into the ground, then we can use it at another time when it's needed, particularly in the late summer. And yeah, and so the idea is the changing climate shifts the hydrograph that way. We'd want to try to shift it back this way, get the water to move more towards the summer. All right, now we get into the Yakima Basin. This is an old 1978 classic figure that shows the three principal aquifers in the Yakima River Basin. I'm going to go through them one at a time. The unconfined aquifer, alluvial aquifer, is at the top. So up at the top, anywhere where the river has flowed, you get alluvium deposited. Here's an example. And that aquifer is certainly up in the tributaries near the river, and really in the whole valleys. It tends to be pretty permeable. As you get up into the tributaries, there's also some glacial deposits there, and they are both reworked by the alluvial aquifers, but also sometimes the glacial deposits themselves are still there. Next down in the basins, in all the valleys, those wintering grounds, you have this post-basalt sediment, also often called the Upper Ellensburg Formation. This is, the sediment itself is very heterogeneous. It can be ash, it can be sand, it can be cobbles, it can have clays. So in terms of its aquifer properties, it's variable, right? But it is a good aquifer. It stores a lot of water, it transmits water. And then beneath that, the bottom, and then up on the hills, you have the Columbia River basalts. I think you should be pretty familiar with those. They're thick sequences. We'll talk about how these basalts, you don't maybe think of a basalt as something that water can flow through, but we'll talk about how these are, in fact, major aquifers. They are the really main regional aquifer. So in terms of water storage in the basin, like what places we can store water, we've got the snowpack. That's a main, people talk about that as the sixth reservoir. There's a lot of water stored in the snow. It's changing with climate, so that's a challenge. And then we have our 5, what seem like really big reservoirs until you put them on the map and see that in terms of area, they're not that big, but those are the 5 Bureau of Reclamation reservoirs. But for groundwater, well, that came out looking a little different. It looks much darker green right here. But anyway, for groundwater, there's kind of three main possibilities. One is these sedimentary basins. So those are the places where we're farming. They mostly have that Ellensburg formation, the post-basalt sediments in them. And then we have the tributaries. So these streams coming in have a lot of alluvial sediment along their floodplains, and they all have fans coming out. And then there's the basalts. And you can see the basalts cover an enormous area. And yeah. So, you know, compare this possibility to these little tiny reservoirs. There's a lot of volume there available for storage. And then on top of that, this is key. We know that some of these aquifers, particularly the basalt aquifers, have been mined, which means we're taking the water out faster than it's getting in. The water levels in those aquifers are going down. And so to me, that fact that you've got large storage volumes, you've got aquifers that have been mined, is just asking for sustainable solutions, getting it so that we're not depleting the aquifer. Okay, so I'm going to talk about two examples of groundwater storage studies that I've done with my students and with Lisa. One is up in the Channaway River. It's a floodplain aquifer, so that's up here. And it's unconfined, right? And the other is down in the Rattlesnake Ridge area right here. And we're looking at the possibility of injection into a confined aquifer, the Wanapum basalt. So we'll start with the Channaway River. The place we've been working all over the Channaway River. I'm going to talk about one specific project, which is on a place right there on the main stem right there, so 8 miles up the river, called the Channaway Valley Family Farm. And a lot of this represents the master's thesis of Joe Petralia. So the Channaway Valley Family Farm is a piece of land, and the outline is right here. That's 215 acres. It was previously farmed for Timothy Hay. In around the year 2000, they had been irrigating from a canal along the road. But in around 2000, they shifted from that irrigation source to irrigating from some ring wells down here and from the ponds. So that's important that the water coming into the groundwater has shifted at the year 2000 and around there. And then in 2017, it was purchased by the Washington Department of Fish and Wildlife, and they began a process of trying to restore the land. One important feature of the land is that it has this large grove of dead cottonwoods or dying and dead cottonwoods on it. And one of the questions they asked, and Mid-Columbia Fisheries also came into the picture and has been very involved in this, is what has killed these cottonwoods and what is going on with the groundwater? And so in order to answer those questions, that we put in a series of 10 wells on the property in 2018. All the wells go through the sediment down to the bedrock, which over there is the Roslyn sandstone, except for well 2. We didn't quite make it on well 2. And they're all depths of about 3.1 to 7 meters, or 10 to 23 feet. So they're not that deep, but they cover the entire alluvial unconfined aquifer. So we were lucky enough to be out there while they were drilling, and watched and cataloged what came up from the drill, as they did it. And this is an example of our piles of sediment from well number 2. But anyway, there were kind of 2 scenarios that we saw. In some wells, you had basically this one had soil. This is the top as you move down. From here on down, all these things that look kind of clumpy there, those are very clay rich or very fine grained sediment. I made this little dinosaur out of it. Like you can mold it, okay? I call it clay, but we can argue about that. So that was one scenario. And then the other scenario was a lot of the wells, you just saw cobbles, like, you know, a little bit of soil on top and then cobbles, true alluvium. And so on the landscape, this is what it looks like. Basically, these three wells all had thick sequences of clay. All these wells down here have the cobbles. And then finally at the river, right here, this is the river. At the river, you've got your bedrock. So at that point, you've cut into the bedrock. So I'm going to look at a cross section going actually down here. I think that's next, yeah. So this is what it looks like, we think, in cross section. My first three wells have all this clay at the bottom, right? And then somewhere between 4 and 3, the clay ends and the cobbles begin. What we think is that this is essentially like a glacial lake deposit that was maybe bigger before, and the river has eroded away into it. This clay is really important hydrologically because it can hold water. It's wet and moist, but it doesn't let water through. So it's not an aquifer, and it takes up a big volume of space that you could maybe store water. Emily, who's giving a talk next week for her master's, is going to talk a lot more about the clay, I'm sure. Okay, so let me move on. All right, now we're going to look at some data. This is water level in all the wells. We put little transducers in them that measure pressure, and you can extract a water elevation from that. And this is 3 years of data from August 2019 to November 2022. In general, I'm just going to tell you what we've picked out as kind of the things to note. Well, one, okay, these are the same plot, except this one is this part blown up. Well, one is much higher. The water level is much higher. It's also not in the floodplain. It's kind of its own aquifer. In all 1, 2, and 3, because of the clay, we think the water is beneath the clay. So it's a confined aquifer. It's got that clay confining it. Well, 2 and 3 are the green ones here. They have a kind of different pattern as well. And so therefore we're concluding that they are in a confined aquifer. And finally, the rest of the wells, which are all these other colors, they all move up and down together. And that represents the unconfined alluvial aquifer. This is a closer look at kind of the patterns in terms of seasons. And this is showing the river and then one of the wells, one of the alluvial aquifer wells. And I divide the pattern into 3 periods. Groundwater recharge. So this is the time when the groundwater is going up. And it starts in the late or mid-fall, and it continues to early winter. So that's the time when water is, the pressure in the groundwater is going up. More water is getting in. Then there's a period when snowmelt is happening, and the groundwater is already starting to decline. The river stays relatively high. So I called that, I think. And then finally, there's this period when the river has this decay and the groundwater plummets. And this is what's known as base flow. It's the time of the year when there's not precipitation inputs to the river. The river is really just being fed by groundwater. And this really extreme drop, I think, is important in terms of telling us how easily the alluvial aquifer, or how easily it lets the water go. Okay, so in this here, so we can take these water levels in the single wells, which is what these numbers are here, and then we can contour the water table to see where is it high, where is it low, and water is going to just want to flow downhill on the table. And this is an example of what the contours look like during that base flow period. So the high is here, the low is there, and so think of a plain. That's the water table, and the water wants to flow basically roughly parallel to the river. When recharge occurs, it shifts. So it was flowing like this. Now it shifts, so it's pointing that way. And the way that happens is, if you look at the numbers, you're getting additional inputs right up here, and it's shifting the angle of that plane. So this is what is happening during recharge. This flowing into the river, that's also called a gaining river, right? Groundwater is rapidly flowing in. This is, sorry, let me go back. Same cross section, right? I think it's the same cross section going down that way. And we're going to look at the same 2 times. This is the cross-sectional view. So I've taken the water levels in those wells and I put them on the cross-section. So during base flow, it's all pretty flat and it's flowing out, parallel to the river. And then you can see recharge. You can see how much more, this is that extra water on this side compared to over here. And it starts to flow more towards the river. The other interesting thing on this cross-sectional view is I show the water level in this confined aquifer that's in well 2 and 3. And down here, it's pretty much similar to the alluvial aquifer, but here it's quite a bit higher. And I think there's evidence in the chemistry that some of this water actually gets out into there. So the big question, and the funding for this has been the question of groundwater storage. So we can look at our data and think of it in those terms. And what this is it's a water level hydrograph groundwater for one well from October 1st to September 30th, so one water year. And in terms of storage, and this is the level of the sandstone bedrock, and that's the ground surface level. It doesn't change throughout the year. So at this point of the year, there's only this little bit of space above the water table where you could put water in. And in general, the amount of extra storage you have in the winter is the difference between the summer and the high in terms of space. In the summer, the best you could do would be to store this much more water. Where I'm heading is I'm trying to put a number on how much water this alluvial aquifer can hold. But I think it's very unrealistic to think that you could ever get the summer water level to be the same as the high, low water level. So in my calculations, which are still incredibly optimistic, I mean, as a potential, I've used about halfway up as a potential storage. Luckily, I don't have time for this equation, but trust me, when I did a calculation, what I tried to calculate was like, on this whole space here, how much water would be sitting there that would be stored in the summer, that could be stored in the summer, if I just spread it out. It's called a uniform thickness. So I take this space, I take some water and I spread it out. How much can I get in there? And I came up with 0.76 meters. That equates to, okay, I have to say what an acre foot is. I have resisted English units a lot, but I've decided that the acre foot is actually a good one. So an acre is a football field, and acre foot is 1 foot of water over a whole football field. So the farmers can talk about this, right? It's a good unit that way. And on this whole spot, it ends up being 125 acre feet, potentially. Lindsay Henning has done a model, and I'm gonna go fast here because I'm running out of time. She discovered in her model, and she's going to present it in 2 weeks if you want to hear more, that the water just doesn't stay in there. So she modeled putting ponds and just putting water into the aquifer using ponds. And by September, they all look the same, whether there's a pond there or not. She'll tell you more about that. So on the Chanaway Valley Family Farm, we've been able to describe how the water is flowing. We now know there's this clay that's important. And we know that there's potential to store some water. We also know that it seems to be flowing out of that alluvium really quickly. So it's a question of whether it would stay there. Now I'm going to move down to the lower Yakima Valley, Rattlesnake Ridge area. So in this project, very different idea here. And the idea is we've got this thick sequence of basalts that we know about. And can we store water in them in a very deliberate way? We put it in with a well or a number of wells, and then we take it out when we need it, usually probably using a well. The Columbia basalts, I think most of you know them. They're an immense volume of basalt flows that cover much of Washington, Oregon, and Idaho. Thick sequences like this. There are 3 main basalt units, the Grand Ronde, Wanapum, and Saddle Mountain, in the study area that we're looking at. So these are the ones that are present in the lower Yakima. Importantly, you have these interbeds, sedimentary interbeds in between the Grand Ronde, Wanapum, and Saddle Mountain. These interbeds are very fine-grained, clay-rich, and they serve as confining layers. So these can be considered kind of major aquifer units. There's certainly subaquifers within them. So let me say a word about basalts as aquifers. I know, a lot of you have been out to see the basalts. You maybe have climbed on them, and they're solid rock, right? They don't seem like they hold water. But in fact, at the top of each flow, you tend to get these brecciated flow tops. They have had vesicles in them. So those broken up zones, and sometimes the sediments that are present with them, are actually really good aquifers. And on top of that, the bigger thing is there's just a big volume of it. There's a lot of space down there. So this is an example from Palouse Falls, where you can see these green zones where water has seeped out. And so that greenness is partly fed by essentially groundwater coming through these permeable zones. Rattlesnake Ridge area, I'll just show you where we are. So Union Gap is right here. Yakima's up here. And Rattlesnake Ridge is just kind of southeast of Yakima. In general, you've got a series of folds here. The units range from Saddle Mountain, Wanapum to Grand Ronde. The next figure is going to be a cross-section right here, east-west-ish. This was done by Bethany Karazi, who's going to also do a presentation. And partly what she did is all these dots here are wells, and she looked at the well logs along that cross-section to see what was in the subsurface. So here's an example. It's a little bit tedious, but it's fun. So when a driller makes a well, they have to submit a well log. And in it, they log what they've seen as they pull up sediment or rock. There's a little bit of reading the tea leaves that goes into interpreting the well logs. But basically, in doing this, she looked for these major sedimentary horizons, and then she decided which of the various Saddle Mountain or Grand Ronde basalts she was looking at. So she did that for all of these wells and came up with cross sections, and here's an example of one. This is that west to east cross section, and importantly for us, this unit down here is the Wanapum. That's our target aquifer. That's where we want to put the water. And you can see it's fairly continuous on this section. We don't, as of now, know of any faults, but it looks like maybe there's a fold, you know, or maybe the well driller, I don't know. Anyway, so the reason we're targeting the Wanapum is it is used primarily for agriculture, and because of that, partly, the water level has been declining the most of the aquifers in that, well, at least more than the Saddle Mountain, which was the other candidate. An average of 0.5 meter a year. It's got more thickness, so it's got more volume of space, and an estimate, just sort of back of the envelope estimate of storage loss is something like 50,000 acre feet per year. Remember, I was talking about 125 on that little piece of plot in the tributary. So we're talking about, this is water that's being lost, that's being taken out and not resupplied. There's this great potential to put water back in. I'm not going to go into detail on this, but except to say, so this is another back of the envelope calculation of how much water could you get in there using different numbers of wells and different input rates. And the big picture and thing is you can put in, and it was a 3-month interval. You can also put in potentially thousands of acre feet. So we can probably get that water back in there. So in this project, we did a lot of background research, looking at the well logs, looking at past reports and so on. And we came up with a plan for some new data that we wanted to collect. We wanted to do some pump tests at these 2 locations, and we wanted to study the water chemistry as well. I'll tell you why. So the idea of a pumping test is ideally you have 2 wells, one of which you pump. And when you pump it, it makes this cone of depression. It comes down. And how quickly it comes down and how quickly it spreads out has to do with the permeability of that rock in the area. So you look at the water in the well that you're pumping and in a nearby well, and you can calculate a permeability. So we went out there to do that. The picture kind of tells you the story of our experience. Bethany's laughing. We lost producers in one well. We got one stuck in a second well, and that's out there reading. And we couldn't even get one into another well. And then, anyway, so it didn't go as planned. We did learn that agricultural wells have things that grab transducer cables and hold them, and that maybe they wouldn't be great for injection wells. We also did manage to measure the recovery after we had pumped. So we did get a little bit of data. Here it is. And we use that data to collect a permeability. And you don't need to know the details of this, except to know that what we measured is consistent with previous estimates. So it's what we thought it would be, and it is suitable for aquifer storage and recovery. Meanwhile, we're collecting water samples. So that's Bailey. This is her thesis project, and Charlie helping out. He's helping out on this. The goals there are to really, there's a lot of regulations. If you inject into the subsurface, there's a lot of regulations about chemistry and quality. Part of the chemistry question is, you've got your rock, you've got your groundwater in there, and then if you add this other chemistry water, there's the potential that some bad reaction is going to happen, like maybe you precipitate something and the pores get clogged up. So we need to kind of model that to see if that's a problem. All right. Conclusions. two promising projects I'm really excited about. I think even groundwater storage wise, they both have their advantages. The Chanaway floodplain aquifer, it doesn't represent a lot of potential amount of water to store. And there's the challenge of keeping it in there. But it certainly, anything that gets done will have a benefit, an ecological benefit, which includes helping with fish habitat. And yeah. For the basalts, I feel like in some ways the sky's the limits. Like I see this as the future of water management in our basin, but there's a lot of logistical, legal, water quality, regulatory concerns here, and it can be expensive. But the permeability seems to be sufficient from what we've seen, and we know that there are these large amount of water that's been taken out. Like it's a reservoir that's been there and we've emptied it, and now we can put the water back in. That's it.
Questions for Carey, and she's going to repeat your questions for the home audience, and I'm going to swap your microphone as well. Who's got a question?
Am I taking this
No,
part?
you're good. Keep this on. Where are you here?
Oh. Catherine.
Catherine.
So I know you were trying to talk around a bunch of different numbers, but in a perfect world, what would you think, like an estimate of how much water we could actually store?
Tens of thousands of acre feet.
Could you repeat the question, please?
The question is, and I was gonna get every single one, but I didn't already. I've watched everyone do that this term. The question was, in a perfect world, how much water could we store? And I think it's the basalt water. I mean, so tens of thousands of acre feet, really. And we talked to the Rosa Irrigation District. That's the irrigation district there. And they actually got a little bit excited about the idea of just putting injection wells right along the canals. And that, to me, I think that is it. Like you find a place that's easy to put it, inject it in, and you want to make sure it's not flowing somewhere you don't want it to, like into the Columbia. That would be a bummer. I mean, nothing against the Columbia, but yeah. Logan.
All right, you say injection wells. How do you actually inject it? Do you just put water in there and let it seep, or you put a bunch of pressure behind that baby and just like?
I think it depends on how much money. Oh, the question is.
Thank you.
I got it.
Thank you.
Before you told me. The question is, how do you inject it into the injection well? And my answer is actually, I don't know. I've never seen it. And I'm going to make up an answer right now. My understanding is, first, you want to just put it in and let it go. Like if it's permeable enough, then maybe that's enough. And then you can put pressure on is the next step. And I'll have to ask my colleagues. They know. A question, yes.
Yeah, what's the efficiency of recovery versus how much you pump down versus?
Oh, that's a very good question. The question is, what is the efficiency of recovery? How much you pump down, you get back. You want it to be 100%. So I think in the basalt in general, it moves pretty slowly. So it depends on when you want to recover it. If you recover it the next day, you're going to have a better efficiency. I think in the basalt, it moves slowly enough that you'd have a pretty high efficiency. But ideally, you look for a place where there's barriers to flow, like folds or something that really stop it, and you can see that it's not going to flow away into the Columbia. And I will say that one thing that you do to start, the next step after we finish our study would be a pilot test where you put it in and see, you would get to see how much it's mounding, and maybe have some wells nearby where you can try to figure out where it's going. But this is one of the challenges of groundwater storage, is it's just not as easy as a surface water thing where you put it in and you know where it is and you know where it's going. Yeah.
Residential rainwater collection,
Huh.
does that put a huge impact on your graph?
No, not really. But I mean, yes, I think it's part, I certainly think rainwater collection makes sense. So in terms of overall water use, your actual like domestic use in the houses is just a very small amount. But there is regulation of wells that are just for domestic use. So any alternative, and then the other part is if you're, well, it would have gone into that alluvial aquifer. You know, you're just collecting stuff that would have gone in. So I think, I guess for me, like on the islands, it really makes a lot of sense because you've got the problem of saltwater intrusion. Around here, it certainly could help supplement a house. In terms of the overall water budget and the big picture, it's not as important, I don't think. Ree.
I'm really curious how you expect the Carey restoration projects to impact groundwater storage throughout the years. Like climate change, all the trees we're putting in right now, they're so small, they're going to get very large, big lots of shade, higher water. How do you think that's going to impact the big picture?
So Ree's question, and I forgot to say the previous.
You're good. You're good.
Is how we expect restoration projects to impact the groundwater storage. I mean, that's been the subject of many master's theses, and I think that Edward and Emily will address that a little bit. In general, the wood is great for habitat. It's great. It depends on where you put it and how much water there is to move it. So there's places like Tainham where they put wood in, and then luckily there was this huge flood and it got moved, and it really changed the habitat, and it definitely changed, at least temporarily, the storage. There's side channels where there didn't used to be. There's beaver dams and ponds. Overall, though, there's the challenge is the late summer, and I think a lot of times it just runs out in the late summer no matter what. The trees help with shade, and that's temperature. So, you know, it's not all just about volume of water. There's habitat from it. And I mean, I think overall, there could be you could push the storage a little bit towards the summer with them. I just think in the late summer, Indian Creek is one place we've looked, and it doesn't look like the logs there made any difference to when the groundwater goes to its lowest. I'm going to let my husband ask a question.
So looking at that graph of the basalt aquifer, it's gone down like 100 feet since 1977. What are the consequences of that for the lower Yakima, or what are the consequences of that?
So his question is the basalt aquifer, the graph I showed, which was one of the more extreme ones, but has gone down 100 feet since 1977. What are the consequences? As far as I can tell, the consequences are that they keep extending their wells deeper right now. There could be some change in, it could be some compression, but I haven't heard anyone say that there is. So it's mostly just emptying a volume of water and having to go deeper to get more. If you look in the well logs right now, all the recent ones are just, a lot of them are extensions of wells. Oh, Bryce.
What does it look like for groundwater storage, like keeping the water in? Like, are a lot of these aquifers good at like holding the water so we don't lose it, or are there ways we can kind of confine an aquifer like manually?
Yeah. So Bryce's question is how good are the aquifers at keeping water? That's a great question, because an aquifer by definition is good at transmitting water, right? And he asked if we can actually artificially confine them. I mean, on a very small scale, you could artificially confine them, but I haven't heard of much about people trying to do that. I mean, I think that you just have to find natural places where they're not, it can keep it. And that's really a lot of our research is that question. I mean, I think in a perfect world, they want us to find a place where you can put water in the spring, and then it magically comes out in the late summer, cool, makes the flows higher and the fish happy. And but I didn't answer your question. I mean, I think that's a question that we're trying to address. Yeah, it's a good question. Eric, did you? Yeah.
How are the cottonwoods? Did you all figure out why they didn't survive?
Oh, the cottonwoods. Eric asked about the cottonwoods at Channelway Valley Family Farm. We think, I didn't mention it, but there's the ponds just up gradient of basically that dead cottonwood grove is where they switched. Their irrigation is from there. And in the late summer, one of those wells in the cottonwood, it goes totally dry down to bedrock. So I kind of think the pumping from the ponds killed that grove. Yeah. Chris?
Kind of as a follow-on, so based on the results of your Channelway Valley Farm research, do you have thoughts for like other of these side stream tributary unconfined aquifers that would be good to explore? Like, in other words, how representative of that is at a basin scale? Are there other sites that might be better suited to the type of storage that you're looking for?
So Chris's question is, based on the Channelway study, are there other, like the tributary aquifers that might be good to look at? So we have been looking at others, particularly the Tainum, and Emily is going to present the Tainum Channelway kind of story as we know it now. Lisa and I are actually right now looking to try to think of, where else to look. There's a little bit of like, I don't know if it's politics or territorialism about where you look, but the places we're looking at right now is Manassas Fan is one place that there's some questions about. Tanum Creek, which runs into below Yakima, into the Yakima. It's one of the tributaries. There's been a lot of work done on Toppenish Creek area, and actually that's the Yakima Nation. They have a lot of plans for storage down in the Toppenish Basin. So they have the most advanced groundwater managed storage plan of anyone. Yeah.
How about one more?
Logan.
Can you combine both injection and groundwater storage? Like drain a reservoir and then put a bunch of wells in there and then fill that back up and solve two problems at once?
Logan's question is if you can take the water out of the reservoir, put it in the ground.
Well, basically just do both groundwater storage and injection at the same time.
Like infiltration,
yeah.
Put it on the surface. The answer is yes. No, the question is, can you do infiltration and injection at the same time? So I think the answer is yes, but and one thing we've been looking at in the basalts is, can we get it in there through infiltration? I don't think you'd necessarily put it in the same place. Like infiltration, you're trying to find a place where it's near the surface and there have to be fractures or some way for it to get in there. I mean, yeah, I think you want to get it in any way you can. I mean, I think that's kind of what we're trying as a larger group, the groundwater storage subcommittee is trying to do, is to try to find out the more places you can get it in, the better.
Just thinking that then you don't have to actually do any pumping. Then that reservoir on its own is already putting it down. In
oh, do it near the reservoir.
In the reservoir.
In the reservoir.
Like
so
bottom of the reservoir, put some wells in there.
The reservoir
screens.
Right, but the reservoirs are up in the mountains. So there's also like,
right,
yeah. I mean, that is, I mean, yeah. So the reservoirs are up in the mountains. The storage, sort of the aquifers up there are not as good. So we haven't really talked much about putting water in the older rocks up in the mountains, really. Yeah.
All right, Logan and everybody. Hey, let's thank Carey one more time. Thanks for coming. We'll see you on June 2nd. That was excellent. I hope you feel good about it. I thought that was just beautifully laid out.
Yeah, thanks.
Yeah.
Yeah, I mean, it's funny, you know how it is. I didn't say, I'd get to some point, I'd be like, oh, I was going to say that 5 slides ago. Oh, well, I guess I didn't, you know what I mean?
No, I thought it was laid out perfectly.
It was a little rushed. Like I looked up when I got to the channel.
You were worried about that. Okay. Great job. Thank you, Carey. Okay, a couple final thoughts for you before we say goodbye. What is going on here? Hang on, hang on. Thank you. Thank you. Okay, you can hear me? I can say just a couple final things. For those that are still with us, we still have 160 watching. Thank you, Elaine. Yeah, there's a real variety in expertise that's here. And I'm hoping that you can see that. And maybe it's a surprise to you. Zoom this in a little bit. Maybe that's a surprise to you that we have, like, I don't know. First of all, have you been in a geology department before? Were you a geology student? Or did you just take a geology 101 class at a college? Or maybe you never went to the university. Okay, any of those, whatever. My point is, many geology departments around the country and around the world have many professors, and by design, the department is well-rounded. So Carey is our groundwater hydrogeologist, isotope geochemist. She also teaches at the 200 level. And, you know, I get interested at the 100 level. We then they continue on in the major, and they have somebody like Carey with some sort of environmental science class or that sort of thing. But perhaps as you start to hear more of these Friday talks with people in our department, and so by now, this year, we've had Hannah Shamlou, early January, if you caught that Friday talk, and then Carey, and then we had both Lisa Ely and Ann Egger talk about women in geology. They weren't really talking about their specializations necessarily, but this is what I'm trying to say before I sign off here with you is that this is a noticeable change. I tried to say it at the beginning. I don't think I said it as well as I wanted to. It's a do-over right now. We have a lot of good things going, and part of it is because of our discipline breadth. And so quite often when someone gets interested in geology and I'm their advisor and they go, I'm really nervous. I don't know exactly what my job is going to be when I graduate in 3.5 years. Like my parents want to know if geology is really a good choice anyway. And I say, it's on purpose that you're not going to know what your job is. You're just going to have faith. You're going to have faith that by the time you get this geology degree, you have classes in all of these sub-disciplines: structural geology, petrology, hydrogeology, geomorphology, geodetics, computer science, glaciology. It's a long list. And we have a big enough department here where we can have people like Carey with her specialization. And she went to Stanford. She's heavily involved in many things, not just groundwater geology, but environmental issues and other things. You know, this is Central Washington University. It's not Caltech. But yet we do have people with very impressive backgrounds, and they have a lot of practice communicating it with our students. So quite often our geology majors are folks who, you know, grew up a couple hours away. They came to Central maybe because it was just far enough away from their parents, but not too far away. And quite often they do not come specifically to study geology. But my point is, within a year's time of taking a 101 class, they're in a hydrogeology class with somebody like that who has depth of knowledge and expertise. And we're proud of that here. So is this a sales pitch? I don't know. I guess all these are sales pitches at some point. But that's the idea, that in addition to our guests who are visiting, we have people right here. And I didn't say it that much. Hey, Gabe, you want to talk? Okay. I didn't say it directly, but hardly anybody in this room, including faculty, had heard Carey speak. She works hard. She works with her students. I haven't heard her give a talk in about 15 years. So it's for us too. It's not just trying to involve other people with the program. Okay, I think that's enough. Gabe the gold miner wants to talk a little bit about, I can guess. But thank you for joining us today. And I hope things are going well with you. There's going to be nothing live here on Fridays until Friday, June 2nd. Feel free to mark your calendar if you want to join us with that. Otherwise, I suppose there'll be a few more geology videos on this YouTube channel coming in the next few weeks, perhaps related to the Cordilleran meeting that I'm going to in Reno, Nevada next week. Baja, BC people. I'll be down there. Otherwise, probably some Ice Age flood stuff coming. Thank you. I love you, and goodbye from Ellensburg, Washington, USA. 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 Goodbye.